Welcome, dear students. Now we discuss about Unit 1, Group B, Biomathematics 2022, Semester 5 CBCS Mathematics Honors, University of Calcutta. Question paper 2022 Mathematics Honors Biomathematics, University of Calcutta, Group B, Unit 1. Question 2A. Write down the continuous time logistic model equation for a single species population and explain the variables and parameters involved. Find the analytical solution of the model equation. Discuss the behavior of population size as time approaches infinity. How does Malthus model become a special case of logistic model? The continuous time logistic model for a single species population is given by dt of n equal to alpha n bracket 1 minus n by k, where in t depends on t time dependent with the population size or density of a species at time t. And alpha is greater than 0 is the linear growth rate, and k is greater than 0 is the carrying capacity of the environment. The maximum possible population, which is usually determined by available sustaining resources, is the first part. Write down the continuous logistic time equation, model equation for single species population, and explains the variables and parameters. Here, the variables, this n is variable, dependent variable, and t is independent variable, and alpha is the parameter, and k is the carrying capacity, is also the parameter. Next, find the analytical solution of the model. The equation 1 can be written as this can be written as k dn by n bracket k minus n equal to alpha dt for n not equal to 0, because if n equal to 0 is undefined. Or this is bracket 1 by n plus 1 by k minus n bracket closed dn equal to alpha dt. Integrating both sides, we get integrating this 1 by n dn plus integration 1 by k minus n dn equal to integration alpha dt plus c is an integrating constant. Log mod n to the base e equal to log mod of k minus n to the base e equal to alpha t plus c. So this can be written as this e to the power alpha t plus c equal to a mod of n by k minus n. Using the initial condition, this is the initial population size in at time t equal to 0, this is equal to n0 say. So we get mod of n0 by k minus n0 is equal to e to the power alpha n0 plus c is equal to e to the power c. And then this modulus of n by k minus n equal to n naught by k minus n naught is equal to e to the power alpha t. Note that the equation 1 has two particular solutions, n equal to 0 and n equal to k for all time t, corresponding to the steady states. Also, this n not equal to 0 or k, initial population size not equal to 0 or not equal to k. So neither n or nor k minus n changes sign on an orbit, and hence the sign of n by k minus n is the same for all time t. So n or k minus n changes the sign on orbit, and hence the sign of this. Neither n nor k minus n changes the sign on an orbit. because initial population size is not equal to 0, not equal to k. This initial population size not equal to 0, not equal to k. So n and k minus n are all time same sign. So we can write this without modulus sign, this n by k minus n equal to n0 by k minus n0 to the power alpha t. This is equal to P.Sc. So we can write this n equal to kp from this first ratio with p minus np, or n equal to kp by 1 plus p, or n equal to from first and second ratio, this k into n0 e to the power alpha t by k minus n0 whole divided by 1 plus n0 to the power alpha t by k minus n0. So after simplification, we can write nt equal to k n0 by whole divided by bracket k minus n0 bracket close into e to the power minus alpha t plus n0. And this is the analytical solution of the model 1. Third part, how does Malthus model become a special case of logistic model? If time t approaches infinity from 2, this equation solution, this nt at t approaches to infinity, so this e to the power minus infinity is 0. So k n0 by n0, n0 not equal to 0, so nt equal to k. So nt tends to k. As t tends to infinity, the population size approaches the carrying capacity k. And fourth part, Malthus model is special case of logistic model. The logistic model is given by ddt n equal to Rn into n. This Rn equals to alpha bracket 1 minus n by k. And the actual Rn is actually Rn equal to 1 by n ddt of n. So 1 by n ddt of n is called the per capita growth rate or actual growth rate. And alpha is the linear growth rate. So logistic model is actually this dn dt equal to r function of n into n. This alpha 1 minus n by k is called Rn, or is a function of n. If k tends to infinity, this Rn tends to alpha, because 1 n by k tends to 0, so Rn tends to alpha. So per capita growth rate tends to linear growth rate. So dn dt equal to alpha n. This is the Malthus model. Here, k tends to infinity implies the resources are infinite. Case 2, if n is less than k, population size is less than carrying capacity, then Rn tends to alpha. Rn is because n by k less than 1, actually 1 minus this approaches to 0, then Rn tends to alpha. So dn dt equal to alpha n. Thus, when k tends to infinity or n less than k, then ddt of n equal to alpha n is the Malthus model. So logistic model tends to Malthus model when k tends to infinity or in less than k. Next question 12 2b. What is an equilibrium point or steady state of ddt of n equal to fn when a steady state called asymptotically stable? Suppose that n star is a steady state of ddt of n equal to fn, and fn is a continuously differential function with f dash n star equal not equal to 0. Prove that n star is asymptotically stable if f dash n star less than 0 and unstable if f dash n star greater than 0. Hence discuss the nature of stability of steady states of the continuous time logistic model for a single species population. This number, this 1 plus 2 plus 3 plus 3. Equilibrium point this steady state or critical point or singular point, consider an autonomous first order nonlinear differential equation dt of n equal to fn. This dt of n, so this is the first order, and this fn, this nonlinear equation mm, is for some continuously differential function fn. A point in star is said to be an equilibrium point or steady state or critical point or singular point of the system 1 if fn star equal to 0. Next, asymptotically stable. The equilibrium point in star is said to be asymptotically stable if there exists neighborhood of n star, that is, we say NBD bracket n star is the neighborhood of n star, such that NT tends to n star as t tends to infinity, where n 0 is equal to n naught belongs to neighborhood of n star, and n naught is the initial value of n. Then we say this equilibrium point in star is asymptotically stable. Alternatively, we can say this equilibrium point in star is said to be asymptotically stable if it is stable. That is, for any epsilon greater than 0, there exists a number delta depending on epsilon greater than 0, such that for all t greater than 0, a norm of n t minus n star is less than epsilon whenever norm of n0 minus n star is less than delta. Or it is quasi-asymptotically stable. That is, there exists a number delta greater than 0, such that limit t tends to infinity, a norm of n t minus n star equal to 0, where norm of n0 minus n star is less than delta. This is the norm, sign norm, Euclidean norm in the space R in n-dimensional space, real space, Euclidean space. For this question, you can write this first part only. Avoid this alternative definition. Next part, third part, stability theorem for single species model. If n star be a steady state of the nonlinear first order autonomous system, derivative of n equal to fn, we call this equation 1. Then n star is locally asymptotically stable if f dash n star is less than 0. Number 2, n star is unstable if f dash n star greater than 0. Number 3, if f dash n star equal to 0, the stability of n star can be determined by geometrically, but not from this theorem. So actually, this is number 3 is the actually is the note, not this. Note this. Consider a small perturbation u t. U is a function of time t, such that ut equal to nt minus n star, where mod of nt ut is less than 1. Very small quantity. Differentiating with respect to time t, we get ddt of u equal to ddt of n. Since ddt of n star equal to 0, n star is a fixed point, then the given equation becomes this ddt of u equal to f of n star plus u, because nt is equal to u plus n star. So expanding by Taylor series about n star, f n star plus f dash n star into u plus f double dash n star by factorial to u square plus dot 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 dot. And since f n star equal to 0, because n star is the fixed point, so this f dash n star u, this neglecting this second derivative and higher order derivatives, higher powers of u square, this because this u is very small, so u square is also small and u cube also small, and neglecting this u square, u cube, and so on and so on. So we get dt of u equal to f dash n star into u, and this is obviously is the linear system of the given nonlinear system 1. So corresponding linear system, derivative of u, if this instant is constant, and this u linear system, corresponding linear system of the given nonlinear system 1. Solution of 2, obviously, this dut is equal to u0 e to the power f dash instant into t, because you can write the dt of u equal to f dash instant u, integrating, we get log u, this log u by c is equal to f dash instant t, this u equal to cx e to the power f dash instant t when t equal to 0, u0 is equal to c. So uh, write, we can write ut equal to this. Here u0, this positive, is the initial value of ut at time t equal to 0. Case 1, if f dash instant is less than 0, from 3 we get ut tends to 0, because u to the power minus infinity, this tends to 0 as t tends to infinity. And this, so in star, because ut equal to nt minus n star, so ut tends to 0. So obviously nt tends to n star at as t tends to infinity when f dash n star is negative. Hence, n star is locally asymptotically stable. Case 2, if f dash n star is greater than 0, from 3 we get this e to the power this positive e to the power infinity tends to infinity. So ut tends to infinity. And so nt does away from n star as t tends to infinity. So the steady state n star is unstable. Next, last part of this question, hence discuss the nature of stability of the steady states of the continuous time logistic model for single species population. Now, logistic growth model is given by ddt of n equal to alpha n bracket 1 minus n by k, this is equal to fnc. If n star be a steady state of the system, then if n star equal to 0, this gives either n star equal to n1 star equal to 0 or n2 star equal to k. So we get two steady states of this logistic growth model. Now, if dash n this equals to alpha, this alpha n minus alpha n square by k, so 2 alpha n by k. Now, if dash at the point 0, this equal to alpha, because this positive, because this alpha is positive, so n star equal to 0 is unstable. And if dash k, this put in n star equal to k, so minus 2 alpha, so minus alpha is negative, so n 2 star equal to k is locally asymptotically stable. So this is the page portrait, this n and this corresponding y-axis derivative of n. So this point 0 is unstable and this point k is stable. For this graph is this arrow towards this point k. Actually, this is the 0 and this point is k, carrying capacity k. Next question. Question 3a. What are defects of Malthus model? Write down Gompertz model explaining the variables and parameters involved. Find the steady states and discuss their stability. Defects of Malthus model. The Malthus model, ddt of n equal to alpha n, predicts that the population growth will be exponential because nt equal to n0 to the power alpha t is the solution of this model. But in reality, this is inaccurate for very long time. The main mistake is that the growth rate alpha, this linear growth rate alpha, is constant, regardless of the size of the population. But growth rate alpha must be depends on the size of the population n. That is, density dependent growth rate is a more realistic situation. Next, second part, write down the Gompertz model explaining the variables and the parameters involved. We write here for single species Gompertz model, this ddt of n equal to RT of n, where growth coefficient RT equal to R naught e to the power minus alpha t, where R naught equal to R at 10 t equal to 0, initial value of R. And alpha greater than 0 is the decay coefficient and support constant, and t is the time, and nt is the population size or density. This the alternative form of this one can be written as ddt of n equal to minus alpha and log n by k to the base e, natural logarithm, where k is the carrying capacity and is given by k equal to n naught exponential r naught by alpha, where n naught equal to n0 is the initial value of n. In this model, population grows with intrinsic rate of growth that decays exponentially, and the population eventually ceases to grow. Stability analysis of this model from the equation 2, alternative form of this Gompertz model, this dn dt equal to minus alpha in log n by k equal to fn same. For steady state in star, we have fn star equal to 0. So uh, alpha n star log n star by k equal to 0. So n star equal to k. N star not equal to 0 because if n star equal to 0, it is impossible. This log 0 undefined. So only one steady state, this n star equal to k, carrying capacity. Now if dash n, this fn is equal to this, so if dash n equal to minus alpha log n by k minus alpha. So if dash at the point k equal to minus alpha, because alpha is positive, so this is negative. Hence the steady state, this n star equal to k is locally asymptotically stable. Next, part 3b. So that for the single natural fish population harvest model, ddt of n equal to Rn bracket 1 minus n by k bracket close minus qen. At q equal to r, there is a transcritical bifurcation where E is the fishing effort and q measures catchability. I draw the bifurcation diagram. Let this ddt of n equal to fn. So fn equal to Rn bracket 1 minus n by k minus qn. For steady states, ddt of n equal to 0. So Rn bracket 1 minus n by k minus qen equal to 0. So either n equal to 0 or from this factor n equal to k into bracket 1 minus qe by r. So there are two steady states, this n1 star, this trivial steady state, and this n2 star equal to this k into this is the non-trivial steady states. Now f dash n is equal to fn, so f dash n equal to r into n into minus rn square by k, so twice n by k minus qe. So f dash for n1 star, that is 0, is equal to put n equal to 0 here, so r minus qe. And if dash into star is this, so put into star is this here, so we get after simplification qe minus r. Case 1, we have to find this qe equal to r. There is a transcritical bifurcation. Now case 1, if qe is less than r, so if dash 0, this r minus qe, this greater than 0, r minus qe is greater than 0. So n1 star equal to 0 is unstable. And if dash n2 star is equal to QE minus R is less than 0, and hence N2 star is locally asymptotically stable. Case 2, QE greater than R, then F dash 0 equal to R minus QE less than 0, that is N1 star is locally asymptotically stable, and F dash N2 star this is equal to QE minus R greater than 0, that is N2 star is unstable. So if we draw this transcritical bifurcation, this axis is QE axis and this axis is N star axis. So first we draw these two lines, this or these critical points, this N equal to 0 and N equal to this. So N equal to 0 is this line, QE axis, and N star equal to K my bracket 1 minus QE by R. This line is this line. We can easily draw this. Now, this point is R. When case 1, QE less than R, when QE less than R, then N1 star is unstable. So this line is unstable. So for unstable, we put here dots. So this unstable N1 star equal to unstable, and N2 star is locally asymptotically stable. So N2 star is this line, this part of this line. So this stable. So arrow towards this line, and this arrow uh, far away from this line, unstable and is stable. And when Q is greater than R, so this N1 star equal to 0 locally asymptotically stable. So this N1 star is this stable, so thick line, and this N2 star is unstable. So this thin line or dotted line unstable. So we draw this graph for steady states N star versus QE. The stable branches steady states with thick lines, and unstable branches with dotted lines, not thin lines, the dotted lines. This DO, TT, ED, dotted lines. Uh, Two branches collide and exchange their stability at the bifurcation point Q equal to R. Collide and exchange their stability, where there is qualitative change in the behavior of the system. Clearly, a transcritical bifurcation occurs at Q equal to R. Next, part 3C. What do you mean by a pitchfork bifurcation? A pitchfork bifurcation is a particular type of local bifurcation where the system transitions from one fixed point to three fixed points. Since its virtual resemblance looks like a pitchfork, it is named such. Example, ddt of x equal to rx minus x cube. And for steady states, ddt of x equal to 0. So x equal to 0. So either x equal to 0 or x equal to plus minus root over of r. So there are three steady states here. Let fx equals to rx minus x cube. Then f dash x equal to r minus 3x square. So f dash 0 equal to r. F dash root r equal to minus 2r. F dash minus root over of r equal to minus 2r also. Case 1, if r is less than 0, there is only one steady state because r is negative, then root over r is a complex number. So there is only one steady state, x star equal to 0, trivial steady state. And this f dash 0 equal to r, and this r is negative. So x star equal to 0, this trivial steady state is locally asymptotically stable. Case 2, if r is greater than 0, then f dash 0 equal to r is greater than 0, x star equal to 0 is unstable. F dash root over r is minus 2r is less than 0. So x2, actually this is the x1 star, we get 3 x2 star and x3 star equal to minus root r is locally asymptotically stable because this f dash minus root over r minus 2r is less than 0. So the bifurcation diagram, this axis is horizontal axis, R axis, and this vertical axis, X axis. For these critical points is R equal to X equal to 0, and from this X equal to 0 or X common, so R minus X square. So R minus X square, R minus X square equal to 0. So uh, either X equal to 0, X star equal to 0. So X star equal to 0 is this line, and from uh, second equation, this uh, taking common this, actually if X equals to this, so we can write X common, so bracket R minus X square, X square. So Ax equal to 0 and R minus X square equal to 0. Actually R, X square equal to R. So X square equal to R. So this is the parabola. First we draw this curve X square equal to R. Now when R less than 0, only one steady state, this X star equal to 0 is locally asymptotically stable, and draw this line, part of this line by thick line. This is stable, so towards arrow towards this line, and after this point R equal to R greater than 0, this X1 star equal this critical point is unstable, so this dotted line is unstable, and this X2 star is the root over of R, and X3 star is minus root over of R, stable line. So uh, bifurcation point are equal to 0, and exchange of stabilities takes place between the steady states. Stable branches of steady states with thick curves and unstable branches with thin line. The above type of bifurcation known as pitchfork bifurcation. Actually, it is the supercritical pitchfork pitchfork bifurcation. Another type is this subcritical pitchfork bifurcation. I'm not discussed here. Thank you for watching this video. This completes this Unit 1 2022 Biomathematics.